Okay, so let's talk about the identity in multiplication. Okay, so what number that when you multiply it with anything else gives you back what you had multiplied it with? 1. So multiplication identity is 1, since any number times 1 gives us back that number. Okay, so when we're talking about the multiplicative identity for matrices, we're only going to do this within square matrices. So for square matrices, the identity matrix for multiplication will be 1 on the diagonal with every other element being 0. Okay, so let's say we have a 2 by 2 identity matrix for multiplication. The main diagonal starts in the upper left. So you put a 1 there, and then you go down on that diagonal. And then everything that's not on that main diagonal starting from the upper left will be a 0. What if we have a 3 by 3? So we have the 3 by 3 identity. We are going to start at the upper left, and on that main diagonal, working its way down from the upper left, will be 1s. Everything else will be a 0. Talk about a 4 by 4. All right, main diagonal starts upper left, and you go down that diagonal filling in 1s. Everything else will be a 0. All right, so let's say I'm going to give you an example. If A is equal to, first row is -1, 2, 3. Second row is -2, 4, -1. Third row is 5, -3, 2. I want us to show that matrix A times its multiplicative identity is equal to A. Okay, so, oh, why'd that happen? I just made it brighter. Okay, so now what I want is I want to look at matrix A, and do we agree this is a 3 by 3? So I'm going to take matrix A, -1, 2, 3, -2, 4, -1, 5, -3, 2, and I'm going to multiply it times its identity matrix, which is a 3 by 3. So upper left is a 1, and then a 1 on its main diagonal, and everything else is a 0. And I'm going to show that when I multiply matrix A times its identity matrix, I'm going to get back matrix A. So this is a 3 by 3 multiplied with a 3 by 3. What is my product matrix going to be? 3 by 3. So now we go ahead and we multiply. So I'm going to take my first row times my first column, and that's going to be my first element. So we're -1 times 1 is a -1, 2 times 0 is 0, 3 times 0 is 0. Now we're going to take that first row, multiply it with our second column. -1 times 0 is 0, 2 times 1 is 2, 3 times 0 is 0. Then we're going to take that first row, multiply it with our last column. -1 times 0 is 0. 2 times 0 is 0. 3 times 1 is 3. Now we move on to our second row. And we're going to have -2 times 1 is a -2. 4 times 0 is 0. -1 times 0 is 0. Second element in this row, -2 times 0 is 0. 4 times 1 is 4. -1 times 0 is 0. Going on to the third element in this row, -2 times 0 is 0. 4 times 0 is 0. -1 times 1 is a -1. And if we do the same thing again, but for the last row, we are going to get 5 plus 0 plus 0, and then 0 plus -3 plus 0, and lastly 0 plus 0 plus 2. So if we add up all those spots, we end up getting -1. Oops, I forgot to put a plus here. -1, 2, 3, -2, 4, -1, 5, -3, 2. So did we show that when you multiply a matrix times its identity, we get that matrix itself? Yes. Okay, so now we're going to talk about the inverse, where the inverse is a little bit more complicated. So the inverse for addition, didn't we just negate the whole matrix? So like if you have your matrix and then you just negate every element in that matrix, won't that get us to 0? Right, so now the multiplicative inverse is a little bit different. So getting to the identity matrix in addition was a lot easier. Getting to the identity matrix in multiplication is a little bit more involved. So the multiplicative inverse is represented by that matrix raised to the negative first power. So I have A raised to the -1. That's called the inverse. And we're going to do this for square matrices. So if I take matrix A and I multiply it by its inverse, we should yield the identity matrix. So let's say I told you matrix A is A, B, C, D elements. So now to find the inverse of that matrix, we ready for this? The inverse of that matrix is going to be 1 over the determinant of matrix A times, now we're going to go back to matrix A. We're going to switch the elements in the first and the last. So I'm going to switch D and put it here and A put it here. And then keep the other diagonal the same, but just negate it. So it will be negative C and negative B. And I'll show you how this works. All right, are we ready? So I'm going to tell you if A, so here's our first example, if A is equal to the matrix 5, 4, 2, 3, find the inverse of A. The multiplicative inverse of A. So remember, the inverse of A will be 1 over the determinant of A times switching the first and last and negating the other two. So the first thing I want to do is find the determinant of A. Who remembers how to find the determinant of a 2 by 2? Bina? You got it. It's AD minus BC. So I'm going to have 15 minus 8, which is 7. So that means we are going to be 1 over 7 times, now I'm going to switch the numbers on that first diagonal, so 3 and 5 switch, and then I'm leaving 2 and 4 in the same positions, but I'm negating them, so negative 2 and negative 4. So now I have a scalar times a matrix. What do I do when I have a scalar times a matrix? Distribute it right in. Exactly. So now my multiplicative inverse of matrix A will be 3 over 7, negative 4 over 7, negative 2 over 7, and 5 over 7. Who wants me to check and show you that this inverse matrix, well, the matrix A times this inverse matrix gives us the identity matrix? Does anybody want to see that? Okay, I'll show you. So remember, we said A times the multiplicative inverse will be the identity matrix. So my matrix A is 5, 4, 2, 3 times my inverse matrix, which is 3 over 7, negative 4 over 7, negative 2 over 7, 5 over 7. So we have a 2 by 2 times a 2 by 2. Do we all agree our product will be a 2 by 2? All right, so I'm going to go ahead. I'm going to multiply this times this. So I'm going to have 15 times 3 over 7, which is going to be 15 over 7, plus 4 times negative 2 over 7, which is negative 8 over 7. Move on to this one. 5 times negative 4 over 7 is a negative 20 over 7, plus 4 times 5 over 7 is 20 over 7. Now we're moving down here. We have 2 times 3 over 7 is 6 over 7, plus 3 times negative 2 over 7 is a negative 6 over 7. And then 2 times negative 4 over 7 is a negative 8 over 7. 3 times 5 over 7 is 15 over 7. 15 over 7 plus negative 8 over 7, isn't that 7 over 7? But what's 7 over 7? 1. Negative 20 over 7 plus positive 20 over 7, isn't that 0? 6 over 7 plus a negative 6 over 7, isn't that 0? And then negative 8 over 7 plus 15 over 7 is 7 over 7, which once again is 1. What is the identity matrix for a 2 by 2? Isn't it 1 on the main diagonal, zeros everywhere else? So it does work. All right, last thing with this lesson. Yes?
What is it used for, the identity?
It's not, for us, it's not really used for anything. Sort of just similar like how we know A is the identity, 1 is the identity matrix number for multiplication, right? It's just something to know. Like, we're never really like, oh, use the addition identity, right? We just know that 0 is the addition identity. Same thing with this.
Is it possible to do division for it?
We do not do division. Actually, when we come to solving linear equations using matrices, you'll see that we can't use division, that we're actually, this is the purpose of the inverse matrix. You'll see that when we get there. Okay, so last thing, we are going to say that matrix multiplication is associative A times B times C, meaning we just move the parentheses, we don't move the order, is equal to A times B times C, A times the quantity of B times C. Matrix multiplication is not commutative. So A times B is not necessarily equal to B times A. Let's talk about why. If A is equal to a 2 by 2, 2, 1, negative 1, 3, and B is negative 1, 5, 4, negative 2. So this is a 2 by 2 and this is a 2 by 2. We can multiply, right? So I'm going to first multiply A times B. Actually, I want this side of the class to multiply A times B, and I want this side of the class to multiply B times A, and see what we get. So this side, A times B, this side, B times A. You guys, A times B, this side's B times A. It's 2 by 2. You're just multiplying. So B first, the matrix B written first, times, then the matrix A written. And then for the people A times B, you write A first, then B, and multiply. All right, who multiplied A times B? Tell me, what did you get? First row. Nobody? This side of the room. Abby?
2 and 8, 13, negative 11.
You got it. All right, this side of the room, who multiplied B times A? What did you get? Guys, this wasn't that hard. Haley, you want to help me?
Negative 7, 14, 10,
All right, these were correct. Are these the same? No, these are not the same. So multiplication is not commutative. That's a huge one here. We need to remember that. Sean, do you need me to multiply it for you?
No, I got it.
You said you didn't get it.
Well,
You found your mistake? Oh, okay. Whichever one said first. So if it's A times B, A has to go first. All right, that's the end of whatever day this was, day 3. Let's go on to day 4. To start day 4.
Oh. So 2 times 5.
1, negative 1 times 5.
All right, so day 4, we are using matrices to solve linear equations.
Wait, no. Yeah, so
You didn't get it? Do you want me to do it?
no, it's fine.
Are you sure?
No, like, it's just probably a dumb mistake.
Antonio, I don't mind.
You should just do it.
Just do it? Okay. Were you A times B or B times? You were A times B, right?
Yeah.
Okay, so for A times B, we were 2, 1, negative 1, 3. 2, 1, negative 1, 3 times B is negative 1, 5, 4, negative 2. Okay, so you want to take that first, sorry, our product will be a 2 by 2. So we're taking that first row with its first column. 2 times negative 1 is a negative 2. 1 times 4 is 4. And then we're going on to the second column. So 2 times 5 is 10. 1 times negative 2 is a negative 2. Now we move on to the second row. Negative 1 times negative 1 is 1. 3 times 4 is 12. Negative 1 times 5 is negative 5. 3 times negative 2 is a -6. So then we end up with 2, 8, 13, -11. You found your mistake?
Yeah.
Okay. All right, so now we are Unit 10, Day 4, and we are solving linear equations using matrices. Okay, so I've been asked now a couple of times, like, what do these matrices represent? And I said, what we were doing before, they didn't really represent anything. They just represented numbers. But matrices in general is just a way to organize data. That's all it is. It's just a way to organize data. So I could actually take these linear equations and I could write them in matrix form. So what I'm going to do is I'm going to set up my first matrix, and my first matrix will be what's on the left of the equal sign. So I'll have an X column, I'll have a Y column. So then that's going to be A1, A2, because it's A1X, A2X, and then B1, B2. So, or you could look at it as my first row is the first the first equation. My second row is the second equation minus the equal sign. And that's going to equal my solution matrix, which is C1, C2. So now if you look at the row, each row, we can translate this back into an equation. A1x plus B1y equals C1. A2x plus B2y equals C2. That's how we translate that back into equations. All right, so how would we use this to solve a system? Well, let's say, oh, sorry, I needed my x's here, so ax, by, b2y, sorry. We needed our x's, y's there. All right, so what I'm going to do is I'm first going to make just a coefficient matrix. If I just made a coefficient matrix, it would be A1, B1, A2, B2. Do we agree that would be my coefficient matrix? And then I'm going to multiply that with my variable matrix, which is just X, Y. And that's going to equal my solution matrix, which is C1, C2. Now think of this as an equation, right? If I know my coefficient matrix, aren't those all real numbers? My coefficients are all real numbers, generally speaking. And then this is my variable matrix. Isn't this what I want to solve for, my variable matrix? And then this is my solution matrix, which is generally also all real numbers. So for me to solve this, I need to isolate my variable matrix. How do I isolate that variable matrix? I need to get rid of my coefficient matrix. But in matrices, you can't divide. In matrices, you can't divide. So what can I multiply my coefficient matrix by to get it to an identity?
Do multiplicative inverse matrix.
Good, we'd multiply it by its inverse. And what I do to one side of an equation, I have to do to the other side of the equation. So, simply put, let's say I have matrix A times my variable matrix equals my solution matrix. And if we want to solve for our variable matrix, we need to get rid of our coefficient matrix. So what we're going to do is we're going to multiply by the inverse matrix on both sides. So I'd multiply here by the inverse, and I'd multiply on the other side of the equal sign by the inverse, but it needs to go before the solution matrix. So these two would cancel out, and we would get x is equal to the inverse matrix times the solution matrix. But the inverse matrix must be first. Right, because we've learned that multiplication is not commutative, right? So it matters the order. The inverse matrix has to be first. Are we ready to try a problem? All right, so first problem we're doing. I want us to solve using matrices. What's Cramer's? Solve using what? So if I'm using matrices here, what's Cramer's use? It doesn't use matrices. What does it use? Determinants. Good. All right, so we want us to solve using matrices. And my system is negative 2x plus 3y equals negative 8. And x plus 2y equals negative 3. So what we want to do is we want to set up our coefficient matrix, which is negative 2, 3, 1, 2. That's going to be multiplied with my variable matrix, which is xy. And that's going to equal my solution matrix, which is negative 8, negative 3. Anybody confused with how I set up these matrices? Where I got any of those numbers from? Perfect. So now when I want to solve for xy, I need to get xy by itself. So I'm going to multiply by the inverse of this matrix times the solution matrix. But the inverse of that coefficient matrix takes some work. So let's talk about it. So if I'm taking the inverse of this matrix, remember it's 1 over the determinant times dA and then negate B and C. So if I want the determinant of this, remember it's AD, or sorry, if I want the determinant of this, it's going to be AD minus BC. So we are negative 4 minus 3, so this is negative 1/7 times, switch D and A, and then negate B and C. Now I'm going to distribute in that negative 1/7. So I'll write it here. So we are negative 2 over 7, positive 3 over 7, positive 1 over 7, and positive 2 over 7. And then I'm going to multiply that by my solution matrix. I'll let you all catch up.
Isn't that negative 3 supposed to be positive 3?
Is it? Did I write it wrong?
Because you negated it.
Which negative 3 are we talking about?
The one that you multiplied by negative 1, 7.
Negative 1, 7 times a negative 3?
Like in the bottom right.
Yeah.
It's
No.
supposed to be negative.
Negate it means make it the opposite. So, going back to our original one, it was originally positive, so you just make it the opposite, which is negative.
I thought it was originally negative.
Okay. All right, are we ready to multiply? So now I have a 2 by 2, and this one is a 2 by 1. Can it be multiplied? Absolutely. What's my solution? What's my product matrix going to be? A 2 by 1. So now I'm going to have, I'll make this a little bit bigger. So I'm going to have my first row times this column. Negative 2 over 7 times negative 8 over 7 is going to be a negative 16 over 7 plus 3 over 7 times negative 3. 3 over 7 times a negative 3 is a negative 9. Oh. Positive 16 over 7. Thank you. And then 3 over 7 times negative 3 is a negative 9 over 7. And now we're going to the bottom row. 1 over 7 times negative 8 is a negative 8 over 7. And then 2 over 7 times a negative 3 is a negative 6 over 7. (16 over 7 plus negative 9 over 7, isn't that 7 over 7, which is 1? And then we're going to have negative 8 over 7 plus negative 6 over 7 is a negative 14 over 7, which is a negative 2. What does this mean? X is equal to what? Remember, it was xy now equals this. So x is equal to 1 and y is equal to negative 2.
When you do the negative 2 over 7 times the negative 8 over 3, that matrix part, what if you can't multiply them?
Meaning it's not, they're not compatible?
Yeah.
I wouldn't give you one where they're not compatible. But then, yeah, then it's no solution. You can't do it.
Miss Alvaro,
Yes.
Why is there a negative 2 instead of a positive 2?
Where are you at?
Swap A and B.
Yeah, I know. But
Which one are you at?
Like right. We're multiplying 1/7 times that matrix.
1.
How come there's the negative 2?
So this was our original matrix, right?
Oh, I wrote it wrong again.
This was our original matrix. You switch the first and fourth
Okay.
and then negate the second and third.
I just wrote it wrong.
Okay. Do you guys want to try one of these on your own?
Miss Alvaro?
Yes.
Do you mind just like showing the solution for like a little bit?
This one? Oh, like go back up?
Yeah, that's
Sure. Right there? Where am I with time? It's 9:31? 21. Okay, guys, last problem I'm going to give you to do on your own. I'll just move this over, guys. So your last one, I want you to solve using matrices. Negative 2x plus y equals negative 6. 3x minus 3y equals 12. And I will tell you the solution is x equals 2, y equals negative 2, in case you run out of time. So this is I still have the other side up for people that were still copying. But this is the new problem that I clouded. I put in a little cloud. So then next class, I will show you how to use your calculator to do all this fun stuff. You'll be blown away with how much easier it is. I'm going to show you how to do the determinants on the calculator, how to solve matrices on the calculator. I'm going to show you how to do it all. All right, I'm going to stop recording because we're not going to be able to go over it.